Hi friends, welcome to our YouTube channel Naraj Academy. The main aim of this playlist is to teach or discuss the previous year gate questions of electrical machines in a very detailed manner. If you are seeing this video lecture for the first time on our YouTube channel, then please go back to our playlist electrical machines previous year gate questions and see the lectures from the starting, so that each lecture concept will be understood in a very clear manner. If you like the content of our video lectures, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video, that direct notifications comes to your mobile. So why to waste more time? So let's get started. Okay, now let's move forward to do the numerical number 6. See the question number here. See the question here. The question says that when a transformer winding suffers a short circuit, the adjoining turns of the same winding experience. Means, suppose the adjoining turns of the transformer winding, if they are short circuited, then what will be the force between the turns? Whether the force will be attraction, or whether the force will be repulsion, or whether there is no force, we need to figure out in this numerical. And this numerical is given in the gate year 1994 for 1 mark. So let's get begin. There is a transformer. For this transformer, there is a winding. The winding is moved in such a manner so that the current is passing through the winding, because we have kept some AC source, so that the current is going to pass through this winding. So before we solve this numerical, let us learn some concepts, so that after learning the concepts, it will be very easy to solve this type of numericals. See, the first thing is, suppose there is a wire. In this wire, there is a current which is going from down to upward direction. Then we need to figure out what will be the direction of the magnetic field around this wire. So to figure out this one, we need to know right hand thumb rule. The right hand thumb rule says that always keep the thumb in the direction of the current. So, and curl the fingers. If you do this one here, I have kept the thumb in the direction of the current and I have curled the fingers. Then this direction in the curl of the fingers will indicate the direction of the magnetic field, because I am closing from in this direction, so therefore the magnetic field will be, the direction of the magnetic field will be in this direction. This is a magnetic field direction. Suppose I have kept in such a way, suppose there is another wire. In this wire, the current is going from up to bottom. Now, same manner, we need to figure out what is the direction of the magnetic field around this wire. So, by using right hand rule, keep the thumb in the direction of the current and curl the fingers. So, if you see carefully, I am closing the fingers, I am curling the fingers in the direction of the clockwise. So, therefore, the direction of the magnetic field will be in this direction. This is the magnetic field direction. This is B bar. So by using the right hand thumb rule, we are able to figure out what is the direction of the magnetic field around a wire which carrying a current I. If the current is a DC nature, if the current in the wire is DC nature, then the magnetic field will be a static one. Means the value of this will be constant. When the distance increases from the wire, the magnetic field strength will be decreased, but at a particular distance R, the value will be always constant. Suppose in the same way, suppose in this wire, if there is a AC current, then the direction of the magnetic field will be always fluctuating like a AC manner. Sometimes it will be in the clockwise direction and sometimes it will be in the anti-clockwise direction, because the current in the wire can be either upward direction or the downward direction in a AC current. Now what I am going to do is, now I am going to place a current carrying conductor in between a magnetic field. Then you will see whether what will be the direction of the force. So whenever we keep a current carrying conductor in a magnetic field, the conductor will experience a force. So we need to figure out what will be the direction of the force. So see here, there is a magnet. The magnet is, this is the north pole and this is the south pole. So always in a magnet there will be no monopoles. Means a magnet will always have a north pole and south pole, but it won't have either only a single one, like north pole only, it won't exist. So For a magnet, always north pole and south pole will always exist. There will be no monopoles. So this is a magnet, right? This is a magnet. So in this magnet, the direction of the magnetic field always will be north, from north to south outside the magnet. So for a magnet, always the magnetic field will be north to south outwards, and in the inward, in the inside the magnet, the direction of the magnetic field will be like south to north. So what I am trying to say is, for a magnet, the always magnetic field direction will be north to south pole outside the magnet, and in the inside the magnet, the direction of the magnetic field will be south to north pole. So these lines, these magnetic field lines are the closed one. So these magnetic lines will be always closed. So now what I am going to do is, between this magnet I am going to place a wire carrying a current I. Let me assume the current is a DC nature. I is a DC nature, means a constant value, and direction is also from left side to right side. So this magnet is going to is going to have a magnetic field from north pole to the south pole. So I am giving it arrows. So this one, black arrows, indicates the direction of the magnetic field from north pole to the south pole, which is outside the magnet. So because here, if you see here, we already know, if you want to figure out what will be the direction of this magnetic field, if you want to know what is the direction of the magnetic field, by using the right hand thumb rule, we can figure out. So please keep the thumb in the direction of the current in the wire and curl the fingers. So I am curling the fingers like this. So therefore, the magnetic field will be from down to upward, like in this one. So in this fashion, right? In this fashion, the magnetic field will be in this fashion. So see carefully, I am keeping the thumb in the direction of the current and I am curling the fingers, so that I am curling from downward to upward direction. So therefore, the magnetic field will be like in this manner. So if you see carefully, these arrows are downward and similarly these are downward. So therefore the net flux will be added, because they both are in the same direction. So if you see carefully in the downward direction, here the downward direction, the magnetic field will be in the upward direction, and again here the flux, here the magnetic field from the pole is in the downward direction. So because of this opposition, here the magnetic field will be very less. So below the conductor there will be a less flux or field lines, but above the conductor there will be a huge amount of flux, because both are in a addition manner. So there will be more flux lines above the conductor and there are less flux lines below the conductor. So therefore there is a lot of pressure upward and there is low pressure downward. So therefore whenever there is a high pressure, so therefore the wire is going to move downward, because there is a lot of pressure. Means lot of force on the upside of the conductor. So therefore this conductor is going to experience a force in the downward direction. So therefore this conductor is going to move downward direction. So no need to remember all these things. By using a small formula also, we can able to easily find out the direction, whether the force will be in the downward direction or whether the force will be in the upward direction. So the formula is here, just remember this one: F bar is equal to I bar cross B bar. Here these are unit vectors. Here F is force, means F indicates the force on the conductor. It is a direction, unit vector, and I is the current in the conductor here, and this above arrow mark indicates a unit vector, and B means magnetic field which is produced by a magnet and its direction. So here cross product. So based on this formula, we will be now easily able to figure out what is the direction. So we know, by using our general analysis, we got the force will be in the downward direction. So now let us use this formula to figure out whether the force will be either downward or upward. So see here, the current will from left to right, this is a current and this is the magnetic field. So now we need to do, this is the B bar and this is the I bar. So now we need to do cross product from I bar to B bar, This is I bar, This is I bar and this is B bar. This is I bar and this is the B bar. So now we need to do the cross product, right? Cross product from I to B bar. So therefore see like this one. So from here to here, from current to field. So therefore this is going to experience a force. The thumb indicates the direction of the force. Therefore this whole wire is going to experience a force downwards. So same thing we got from our analysis also. So one more concept we will learn, and this is a small concept and this is a small convention also. See, whenever the current which is going inside the board, whenever the current which is going, suppose there is a wire like this, imaginary wire, suppose there is a wire like in a vertical manner, in this manner. So whenever the current is going inside this board, then we will represent it as a cross mark. So whenever the current which is coming outside the board, then we will represent it as a dot. So whenever the current which goes inside, then we will write it as a cross, and whenever the current which comes outside, then we will dot mark. So this is easy to remember also. Suppose if you are confused if the current inside is with a cross or dot, suppose if you are confused, then I have made small thing which will be very useful to know also. Suppose I have made like this. This is like a, so whenever, suppose this is a pen, in the front side there is a small nib point and the backward there is a small cross mark like this. It's like arrow. See, suppose this is the current. This is the current. If this current is going inside, then from the outward we are able to see a cross mark. So that's why I wrote it as a cross mark. Suppose if the current is coming from towards us, if it is coming outside this board, then the current has to direction. So if you see from here, we are able to see only the point, nib point. So therefore I wrote it as a nib point. So now with this small thing we are able to remember, if the current is going inside the board, then we are able to see a cross marks. So write it as a cross mark. So whenever the current which is coming outside the board, then we are able to see like this. So we are able to see only the point mark, nib point. So therefore I wrote it as a nib. So this is a small convention. With this convention, with this figure also, now we will be able to remember for lifelong, so that we won't be able to forget this small concept. So what I am trying to do is, suppose whenever the current is going inside this board, by using right hand thumb rule we are able to figure out what is the direction of the magnetic field. So as the current is going inside this board, so keep the thumb in direction of the current. So I am curl the fingers. So if you curl the fingers, you are curling in a clockwise direction. So therefore the magnetic field around the wire is in a clockwise direction, which is B bar, in a clockwise direction. Suppose if the current is coming outside the board, right, means outside the board means keep the thumb in the direction of the current. So I have placed the thumb which is outward the board and curl the fingers. So if you curl the fingers, the fingers are curling from the anti-clockwise direction. See carefully, anti-clockwise direction. So therefore we need to write in a closed form. So therefore the direction of the magnetic field will be in a anti-clockwise direction. So now what I am going to do is, now I am going to place two wires. I am going to place two wires and I am going to pass the current through them. Suppose the direction of the current is the same to the both wires is same, then what will be the force between them? And if the current direction is between the wires in opposite direction, then we will see what type of force exists between these two wires. So in the first case, what I am going to do is, I am going to place two wires. Let me assume this, and this is a wire A and this is a wire B. So in the first case, what I am going to do is, I am going to send a current. I am going to send a current in the same direction. In both the wires, I am going to send same amount of current also in the same direction. So what will happen? See, I am going to pass the current from downward to upward in the wire A, and similarly same amount of current I am going to pass through the another wire B from downward to upward. So therefore these two wires having same current and also same direction. Now we will see what type of force exists, what type of force will be between these two wires. So I have told already the formula is F bar is equal to I bar is unit vectors. All these are unit vectors, right? Unit vectors. So by using right hand thumb rule, the direction, keep the thumb in the direction of the current and curl the fingers. So if you curl the fingers, you will be able to see that the direction of the magnetic field will be in this direction, right? And similarly, same direction, right? So therefore curl the fingers like this. Similarly here also same direction, right? Same way of the magnetic field direction. Now what I am going to do is this, because of the current in this wire and because of this current there will be a magnetic field on this wire. So what will be the direction of the magnetic field here? It will be downward, right? It will be downward. See, from here it is going up to here and it is going to come inside because arrow is inside. So here it will be again like this, right? So similarly again at this point there will be a magnetic field will be inside to it. So therefore the magnetic field will be inside, means like this. Suppose this black one indicates cross mark indicates the direction of the magnetic field at this point. At this point the direction of the magnetic field because of the first wire is inside this wire is going inside. So that's why I made it a cross. And similarly the current is upward, right? So the current is upward, means let me assume this is B bar and this is I bar. This is I bar and this is B bar. At this point the current is upward and the magnetic field due to first wire it is inside. So now we need to do I bar cross B bar. This is I bar and this is B bar. So I bar cross B bar. Now this thumb indicates the direction of the force. This force is towards the left side. This one is left side, right? This is right side. So the force is left side. So therefore the force is here. The force, because of this wire, there is a force on this wire. The direction of this force is this one. And similarly now we will do what type of force on this wire because of this wire, means so same thing again we will do here. See carefully, if you are not confused, see it again, to be very easy. See what I am trying to say is, so now there is a point P. There is a point P, right? Now because of this current the magnetic field will be again in this direction. See carefully, the direction of the magnetic field will be in this direction. The magnetic field will be in this direction. So say for at this point also like this. So now I need to figure out what will be the magnetic field because of this wire at this point, the direction. So similarly here it will be like this, right? So the direction will be outward means dot. So at this point P, the direction of the magnetic field because of this wire at point P is outward means dot. So but the current in this wire is upward. So let me assume the current at this point is upward, and the magnetic field will be in this direction. This is the magnetic field because of this wire across this point P, and the current in the point P is downward, is upward. Now I need to figure out what is the force exerted on this wire because of this wire B. So F bar is equal to I bar cross B bar. So this is I, this is B, right? I bar cross B bar, I bar cross B bar, I bar B bar. So curl fingers from I bar to B bar. So I bar to B bar. So the thumb indicates the direction of the force. So therefore the force direction is to the right side. So therefore this wire is going to exert a force in this direction. So if you see carefully, both this wire is going to exert force this side and this wire is going to exert force on this wire right towards this direction. So therefore this both going to attract, and finally they will become like this. Suppose initially if they are in a straight manner and finally they will be like this. This is a wire A and this is a wire B. They are going to come close each other. They are going to come to close. So now we will move forward for the another case. The case is, suppose there are two wires. These two wires, suppose in the wire A, the direction of the current is from down to upward, but in the another wire B, the direction of the current will be in the opposite direction to the previous one. So this direction is from up to bottom. Now we will figure out what type of force exists between these two wires. So this wire, so if you want to figure out what is the direction of the magnetic field across this wire, so by using right hand thumb rule we are able to figure out. So please keep the thumb in the direction of the current and curl the fingers. So if you curl the fingers, we can easily see that the direction of the magnetic field across this wire is in this direction. And similarly, if you want to figure out what direction of the magnetic field in this wire, so keep the finger downward, keep the thumb in the downward direction because the current is going from up to bottom, and curl the fingers. So now we will be able to get the direction of the magnetic field will be in this manner. So now I need to figure out what type of force exists on this wire because of this wire. So now I need to figure out what is the formula. F bar is equal to I bar. These are unit vectors. So therefore now what I am going to do is, this wire is going to, we know what the magnetic field direction is like this, right? So up to now just forget about this magnetic field, nature. Now same thing will happen again, same direction magnetic field, but if you see across this point P, let me assume the point P, so therefore the magnetic field direction will be inside that P, right? So therefore because of this wire, the magnetic field at point P at this wire is in the inside direction, inside, right? The arrow is going inside. So therefore let me assume inside means always cross. The magnetic field will be inside, but the current is at point P is going from up to bottom, so therefore the current is a downward direction. So let me assume this blue at point P, this blue indicates the direction of the current and this black indicates the direction of the magnetic field. Across the point P, the magnetic field is going inside and the current is going downward. Now I need to figure out what type of force exerts on this point P because of this wire. So F bar is equal to I bar cross B bar. So I is this one, I bar, and this is the B bar. Now I need to do the I bar cross B bar. So move the fingers, these curl fingers from I bar to B bar. So this thumb indicates the force. So therefore the force is in the right side. On this wire there is a force like this. This is a force. So now I want to figure out in the same manner. Now I need to figure out what type of force exerts on the wire A. This is wire A, this is wire A, and this is wire B. So because of wire B, what type of force exerts on this wire A, we need to figure out. The same manner, same thing, we need to do it again. So now we need to figure out let me consider this is point P. So now across this point P, what is the direction of the magnetic field because of this current in the wire? So we already know the magnetic field direction is in this way, right? This way. So this is the magnetic field direction. This is the magnetic field direction. This way, right? This is the magnetic field. So similarly again, this is again P bar. So now I need to find P at P, right? So it will be again like this. So this is so if you see the point P, it is going inside. It is going inside. Inside means cross. Right? Inside means cross. But the current is in the upward direction. Current at point P is in upward direction. So if you indicate this blue one as a current and this black as magnetic field, so now I need to do I bar and B bar. I bar and B bar means I bar to B bar. So the direction of the force is again to this side. So therefore this is the force exerted on wire A due to wire B. So if you see carefully, these two wires are going to get a repel. This wire is going to exert force on this wire to the right side, and this wire is going to exert force on this wire in this left side. So therefore finally, suppose initially if they are like nearby there, same current direction but then opposite. So now finally what will happen means the wire will be like this. They are going to get a repel. So finally what I am trying to say is, whenever whenever both the current directions are different, there will be a force of repulsion direction. Suppose if the direction of the current is same in both the wires, then there will be a force of attraction. I am repeating it again. Whenever the current direction is same in both the wires, then there will be a force of attraction, and if the current directions are different, then there is a force of repulsion. So with this concept we are able to solve this numerical in a very easy manner. I hope you understood all these small concepts. These are the small concepts. If you understood these small concepts, then we can solve this numerical in a very easy manner. So for this transformer, there is a winding. So for this winding I have passed the current. So therefore the direction of current will be like this. So therefore the direction of current in these turns will be in this manner. So if you again see carefully, across these two adjacent turns, the direction of the current is same. Means I have already told you, whenever the direction in the two wires is same, then there will be a force of attraction. If the two turns, if the current direction is different in the two turns, then there will be a repulsion. But in these two turns, adjacent turns, there is a same direction of current. So therefore these turns, the turns are going to experience a force of attraction between the turns, two adjacent turns. So therefore, so now what is going to do is, suppose across these two turns there is a short circuit. So suppose this is a short circuit, right? So suppose there is a short circuit between these two wires, two adjacent wires. So what is going to happen? But previously there is a small wire winding across this one. So the current, because this is the length of the wire is more, so resistance is directly proportional to length. So whenever the length of the wire is more, the resistance is also more. So therefore this wire has the backside wire has a lot of resistance. So therefore the current in that wire, it will be very less. So therefore the current is going to pass through this. So similarly again the current will pass the same way in the previous one. So what I am trying to say is, the current in the backside wire is 0. The current will flow through this short circuit, and again it flows in the same direction. So in the previous case and now, the direction of current is again in the same way. So therefore these two wires, the direction of current is again same. So therefore these two wires are going to experience a force of attraction. So finally again there is a force of attraction before short circuit and after short circuit. The direction of the current is not changed because the backside wire length is more than the short circuit. So therefore the resistance is more. So therefore the current is very less. So therefore it means there is a high amount of current is passing through this short circuit, and it again passes through this normal wire again normally. So again the direction is again same as the previous case. So therefore the direction of the current is same between the two adjacent turns. So therefore these are going to experience a force of attraction. So therefore the final answer is, before the short circuit and after the short circuit there is no change in the force, means there is a force of attraction. This is the final answer. This is the final answer of this question. Suppose if you not understood the concept, then please go back to the starting of this question and see it. You will be able to understand in a very clear manner. Okay, now let's move forward to the numerical. The numerical number is 7th. See the question here. The question says that a voltage V is equal to 400 sin 314.160 means 314.16 T is applied to a single phase transformer on no load. So at no load condition of a transformer, we are going to give a supply voltage V is equal to 400 sin 314.16 T. So at this no load condition, if the no load current of the transformer is 2 sin 314.16 T minus 85 degrees. So at this no load condition, there is a no load current expression they also given, which is 2 sin of 314.16 T minus 85 degree. So now the magnetization branch impedance will be approximately. So he is going to ask what is the magnetization branch of this at this no load condition. This question is given in the GATE year 1997 for the 2 marks. So they are given a supply voltage and they are also given a no load current. The only thing is we need to find what is the branch impedance. this no load branch impedance we need to find in this numerical. So I have drawn the figure. So if there is a transformer at no load condition, means there is load is not connected across the secondary side. So therefore this is an open circuit. Now there is a supply voltage which is connected to the primary side. The voltage is, the expression of the voltage is 400 sine of 314 minus 314.16 T. This is the given, where omega is equal to 314.16. Here at this is actually a closed circuit, right? The primary is a closed circuit. So therefore this circuit is going to pass a current, because whenever there is a closed circuit the current will flow. So therefore the expression of the current at no load, the current drawn is called as a no load current, because the load is no load, means no load condition. So therefore the current drawn is called as the no load current. So therefore the expression of the no load current is already given in the question, which is I naught of t is equal to 2 sine of 314.16 t minus 85 degree. If you see carefully, there is a sign and there is also a sign. Here this current is going to lag, because there is a minus 85, means the current is going to lag the supply voltage, means this is an inductive circuit at the no load condition. So the equivalent circuit of transformer at no load condition will be like this. So therefore the no load condition, the equivalent circuit of the transformer at no load condition will be like this. So this is actually, if there is a short circuit or if you connect a load, then we need to keep another branch here, but there is a no load condition, so we don't have to consider this right side part. But here we have kept a voltage which is V of t. This is a V of t, right? We have kept a current, and this is a current which is I naught of t. So now this is a equivalent circuit, but this is a physical diagram, and this is a equivalent circuit. So this resistance is called as a RC. This is a core loss resistance. So because there is a current flowing, because of this current there is a flux. There is a flux in the core. So because of this flux is flowing in the core, there is a two losses, which are hysteresis losses, and there is a eddy current losses. So therefore because of this hysteresis loss and eddy current loss, this two summation is called as the iron loss. Iron loss means core loss. So this RC is responsible for that. Because of this RC, this iron loss or core loss is occurring on the core. So that's why we have represented it as a RC. Even at no load condition there is a loss. So that's why at no load condition also we kept RC. This RC indicates the loss, which is iron loss. And there is a small inductance which is XM, because even at no load condition there is a flux in the core. So because of this flux there will be induced voltage in the secondary. So but whenever if we keep any load, then only the current will pass. But there is always an induced voltage, because the flux is always alternate in quantity. So therefore this inductance represents there is a flux in the core. Because of this inductor will be, so whenever there is a current flowing through the inductor, means there will be a, I have already told in my previous example also, XM, the value of XM is more greater than the X1 and the X2 dash. If you see the previous lecture, I have told you XM is more greater than the X1 and X2 dash, where X1 and X2 are the leakage reactance, and XM is this XM. This is what I have XM. This XM is what? It is the reactance because of the flux which is linking the primary and the secondary. This is called as a useful flux. Because of this useful flux, there is an inductance between the primary and secondary. So this is what XM. So now we need to find this parallel branch, right? Now we need to find what is the equivalent impedance. So therefore I am going to replace this whole thing by a small element which is Z. This is Z, right? So I have replaced this parallel combination. That is what they are going to ask. Find the impedance of this parallel combination. So this is Z. So now I am going to write it in a phasor form. So therefore no need to do in a time domain. So now phasor representation always takes a RMS value. So the phasor representation will always consider the RMS value. So therefore now I need to write the phasor expression for the voltage. So Vm by root 2, Vm is 400. RMS value of any sinusoidal quantity is Vm by root 2 or Im by root 2. Here we are considering the voltage. That's why Vm by root 2 means 400 by root 2 angle 0. This is the angle 0 because I have taken sin as a reference. So therefore 0 degrees. Now I need to write the expression for the current. Current is equal to, so this is Im, right? So this is sinusoidal. So therefore Im by root 2 means 2 by root 2. 2 by root 2. 2 by root 2. Here there is a minus. Both are sine and there is a minus. So therefore we need to write minus 85 degree. So now we know the voltage, we know the current. So therefore we need to write only impedance. So by KVL we know V is equal to IZ. By KVL V bar is equal to I bar into Z bar. So therefore we need Z bar, right? So Z bar is equal to V bar by I bar. So V bar we know phasor representation is always take the RMS value. So 400 by root 2 angle 0 degree. And I bar is equal to 2 by root 2 angle of minus 85. So if you do simplification, root 2 cancel. So 400 by 2 is equal to 200. So this downward will, if we go up forward, it will become plus 85. So therefore the parallel branch impedance is 200 at an angle of plus 85 degree. Means if you see carefully, positive means, right, positive means there is a resistor and there is a inductor. So therefore inductor means this is an inductive circuit. That is the reason the current is in an inductive circuit, the current is going to lag the supply voltage. So therefore the final answer Z bar is equal to 200 at an angle of plus 85 degree. So after solving the previous problem, now let's move forward to do another numerical. The numerical number is 8. So see the question here. The question says the core flux of a practical transformer with a resistive load. Means they are going to ask what is the nature of the flux in the core when there is a resistance load which is connected to the secondary side of the transformer. So this question is a very simple question, but we will learn more concepts in this so that if any different type of questions are asked on this concept, then we can easily solve this one. So I have drawn this figure to explain the concept. See here, this is a transformer. For this transformer, I have connected a turns to the primary and turns to the secondary. So for the primary turns I am going to supply voltage which is V, which is AC voltage. So for the secondary side I am going to keep 3 loads. So therefore I am keeping 3 loads in parallel because always if you see near your home there is a transformer. All the houses which are connected to this transformer are in parallel connection because suppose if one home is getting short circuit, so therefore the current in that home is 0. So but even that condition also the other homes are going to get the voltage because they are connected in parallel. So therefore the other homes can get even same current. The other homes can get current even when your home is not getting current because for your home there might be some problem. So that's why all the homes are connected in parallel. Suppose if they are connected in series, suppose just in case if your home is, suppose in your home the current is 0 because of open circuit, so therefore all the homes will not get current because the current is 0 because this is series connection. That is the reason always all the homes are connected parallel across the transformer. So that's why I have taken 3 loads, load 1, load 2 and load 3. So I have kept a small switches so that I can on or I can off those loads across this transformer. So this is the main switch. See, now I am going to open this switch so that therefore as you see the secondary is a no load condition because the current in the secondary is 0. So that is the reason this is a no load condition. So now, but even then the circuit, the primary circuit is a short circuit. Sorry, it is a closed circuit because of closed circuit there will be a current I0 because this is a no load condition. So therefore this current I0 is called as a no load current. So because of this current we can write the direction of the current in these terms. So therefore if you want to figure out what is the direction of the flux in this core, we can figure out by your thumb indicates the direction of the flux and the curls indicates, the finger curls indicates the direction of the current. So the current is going from left to right. So therefore curl here, this arrow, this indicates the current. So therefore this indicates the flux direction. So therefore arrow indicates the flux. So now let me assume at this no load condition the flux in the core, because the voltage is sinusoidal, so therefore the current is also sinusoidal, so therefore the flux in the core is also sinusoidal. So let me assume at no load condition the flux in the core is sinusoidal. So let me draw the diagram. Here this is the +1 and this is the -1. So here flux means Weber, the unit of flux is Weber. So now this is at no load condition, this is at no load condition, NL means no load condition. So now what I am going to do is, now I am going to do a keep a load, so therefore I am going to short circuit, I am going to close this switch. So what happened, now I am going to apply only load 1, not the other loads. So therefore I am going to keep the on the load 1. So load 2 and load 3 are in off condition. So because now it is a closed circuit, right, so current has to produce. So now we need to figure out what is the direction of the current in the secondary. This can be figured by the Lenz's law. Lenz's law says that the current will produce the secondary, so that the flux produced by this secondary has to oppose the original flux. The original flux is in the left to right. So therefore by drawing this one, it is a closed, right? So the flux in the core is in the clockwise direction. I assume like this because the current is the right side, so therefore the flux is also in the clockwise direction. So now this winding has to, so now this winding has to produce flux in the upward direction, because it has the original flux in downward direction. Now this winding has to produce the flux which opposes, so from down to up. So now I am going to curl the fingers. So the current has to be in this direction. This is the current direction. So keep the fingers in the direction of the current and keep the arrow thumb. So therefore the thumb indicates the direction of the flux. So therefore the flux produced by this winding is, let me assume this is the flux. This is the magnitude of the flux, direction of the flux and also some magnitude. So therefore this flux, let me assume this is some small flux is going like this, small flux. So therefore the flux in the core, so therefore this flux will be produced in the core, so that it will pass us through the core in this direction like arrow. So blue arrow indicates, so let me assume this is a black arrow. Black arrow indicates the direction of the flux due to original winding, which is primary winding, but due to this current there will be produced small amount of flux, which is red mark. This is a very small amount of flux. This flux will oppose the original flux. So now what will happen, this is a black one, right, this is a black one, this is a black flux and this is a red flux, very small flux. So because these two are in opposition, so therefore this black length will decrease, so therefore the flux will decrease, right, little bit amount of decrease. So because of this decrease, so now EMF will decrease, because as the flux decreases, so therefore the EMF will also decrease. So as the EMF will decrease, so therefore there will be a huge amount of current. So whenever there is a decrease in EMF, see, let me suppose ideally there is no connector ideally has resistance 0, but practically every connector has small amount of resistor. So let me assume there is a small resistor R. See here, the expression of the current I0, is equal to V minus E by R. So therefore as E decreases, V minus E is going to increase. So therefore I0 is, as R is constant, so therefore so as E decreases, the current I0 increases. So as I0 increases, I0 is directly proportional to flux. So therefore again, as the flux increases, it again comes back to its original value. Suppose what I am trying to say is, before no load condition, let me assume the flux magnitude is +1. After keeping the load 1, because of this red flux, the magnitude became, let me assume this is 0.95. It became 0.95. So therefore here EMF will decrease, so therefore current drawn will increase and the flux will increase back to the original value. So therefore again it will become again +1. this all thing happen in a fraction of milliseconds. All this phenomena will happen in a very fraction of milliseconds or microseconds. So therefore what I am trying to say is the flux in the core will become same again, same curve, even at no load and also at the loaded condition. So this is the flux diagram or flux equation will be always same at no load and at load. So suppose again what I am going to do, again I am going to keep another load. So when these two loads are in parallel, whenever two resistors are connected in parallel, the resistance will decrease. So therefore the net resistance will decrease. So whenever the resistance will decrease, the current will increase. So again the current will increase. So therefore red arrow length will again increase. Red arrow length will again increase means opposition will again increases. So now it becomes what? Now it becomes, suppose previously it is +1, now it is increased, again this red value is increased. So therefore these two arrows are in opposite direction. So therefore the net value will again decrease. Suppose previously it is +1, then it will become 0.85, let us assume. So again EMF will decrease, current will increase, again flux will increase back to its original position. So again +1. So again you keep another load, same thing will happen. So if you keep another load, three loads are connected in parallel. So therefore the net resistance will decrease. So again more current will be drawn. So that is the reason loads are connected in parallel, the current is increased. So it means whenever the load is increased means we are connecting the loads in parallel. So therefore the current is again increased. So again current is increased. So again the opposition flux increases. So then the net resultant flux will decrease. Again EMF will decrease. Again the current will increase. Again the flux will increase back to its original position. So always the flux in the core is always same thing at no load condition and also at the loaded condition. So this is what I am trying to say finally. See, is at no load condition, at loaded condition, the amount of flux or the equation of the flux in the core is always same at no load and loaded condition. I hope you understood the procedure how to do. Suppose again I am telling you, repeating again, listen carefully. If the load is increased, the opposition flux will increase, so therefore the resultant flux will decrease, EMF will decrease, again current will increase, so therefore the net flux again increases back to the original position. So this is a final concept. So therefore the answer for this question is irrespective of load, what type of load you keep, no matter with resistor or inductor or capacitor, no matter how many loads you keep, the flux in the core is always constant irrespective of the load. Now we will move forward for the 9th question. See the question here. The question says that if the primary line voltage rating is 3.3 kV on the star connected side of a 25 kVA. Now star to delta transformer, the per phase turns ratio is 5:1. Then the line current rating of the secondary side in ampere is. So the question says that there is a transformer which is having a star connection on the which has a star connection on the primary and there is a delta connection on the secondary. This is a 3-phase transformer. So the rating of the transformer is 25 kVA. So now they are given 3.3 kV, means the line voltage of the star connection side. So now they want to ask what is the line current of the secondary side, means the delta connection. On the delta connected, what will be the line current they are asking. This is a very simple question. Let us do this numerical. So I have drawn the question again. This 3-phase transformer, the primary side is connected in a star connection and the secondary side is connected in a delta connection. Here they have given the voltage. Always the voltage indicates the line voltage. So therefore for the star connection the line voltage is 3.3 kV and these are also RMS values. So now they are asking what is the line current. Let me assume this is I2. I2 is the line current. So always this line current is also RMS value. So they are asking what is the value of the I2. The rating is 25 kVA and the turns ratio these are the first phase turns ratio. Means phase means these are the one phase, second phase and third phase. Similarly, one phase, another phase and another phase. So means suppose these turns ratio are 5:1 means suppose in this winding there is one turn, it means in this corresponding winding there will be 5 turns, means 5 times more than the secondary side turns. So now I need to find what is the phase voltage. Phase voltage means line to neutral. Line voltage means line to line. So in a star connection, line voltage is always equal to root 3 times the phase voltage. But now I need to figure out what is the phase voltage. So therefore the phase voltage is equal to line voltage by root 3. But line voltage is already given, which is 3.3 kV. So therefore 3.3 by root 3 kV. So therefore this is the phase voltage. So therefore the phase voltage is, this is the phase voltage. The phase voltage of the primary side. Primary side means, let me assume this is a 1. So therefore this is a 1 means star connection side. Now I want to figure out what is the phase voltage of the secondary side. Let me assume this is phase voltage of the secondary side. Now I want to figure out. So therefore by using simple turns ratio, suppose this is as a turns 5 times of the, suppose these turns are 1 means it will be 5 times more. So therefore V1 by V2 is equal to N1 by N2. So therefore here this phase voltage is VPH of 1 and this phase voltage is VPH of 2. So therefore phase voltage of primary star connection by phase voltage of delta connection is equal to turns ratio. This turns ratio is 5 and this turns ratio is 1. So therefore 5:1. The 5 by 1. So we need VPH2, right? So therefore VP phase voltage of delta connected is equal to VPH of 1 by 5. So now VPH of 1 we know is 3.3 by root 3 kV. So therefore now we will get 3.3 by 5 root 3 kV. So the phase voltage of the star connection is 3.3 by root 3 kV. Phase voltage of the delta connection is 3.3 by 5 root 3 kV. So now in a delta connection, line voltage is equal to phase voltage. So therefore phase voltage is equal to line voltage. So we know the line voltage. We need to calculate what is the line current. Simple. So therefore for a 3-phase transformer, we know that an expression is complex power, magnitude of the complex power, always the magnitude of the complex power is equal to root 3 times the VL and IL. So here we can use either star connection or the delta connection. Suppose if they are asking what is the line current in the, if they are asking what is the line current in the star connection, suppose this is I1. Suppose this is I1. I1 is the line current in the star connection. So yes, we know S is equal to 25 kVA. We know root 3 VL. VL of the star connection is 3.3 kV. So only thing is IL. IL means here I1. So we can calculate the value of I1. But here they are asking only what is the line current in the delta connection. So therefore now we need to apply this one for the delta connection. So S is again same 25 kVA. 25 kVA means 25 into 25 kVA. Here kilovolt and the here voltage is also kilovolt, right? So therefore they will get cancelled. Here kilovolt and kV will get cancelled. So that's why 25, right? 25 is equal to root 3 into VL. VL means here secondary side, right? Line voltage for delta connected line voltage is equal to phase voltage. So VPH of 2 is equal to 3.3 by 5 root 3. Here kilovolt, right? Kilovolt again kVA. So kilovolt get cancelled. Only ampere will remain here. So therefore IL is again your line current is I2. So therefore if you do the simplification, only I2 is only the unknown parameter. So therefore I2 is equal to 37.8 ampere. So here The main thing is S is equal to root 3 VL IL. This is an expression we need to remember to solve this type of problems. If they are asking what is the line current in the star connection, then S we know, VL we know, only thing is I1. So but they are asking this problem to find the line current of the delta connection, so therefore S we know, VL is also we know. For secondary side we need, for the delta connection side we need to use this formula. So I hope you understood this numerical. So after solving the previous problem, now this is the last question of this numerical. This question number is 10 and this is a very interesting question, so please listen carefully. See the question here. The question says that the load shown in the figure absorbs 4 kilowatt at a power factor of 0.89 lagging. See, in this figure there is a load Z. This load is going to absorb power of 4 kilowatt at a power factor of 0.89 lagging, means there is a lagging load. Z is a lagging load. So now assuming the transformer to be ideal, the value of the reactance X to improve the input power factor to unity is. So they want to find what is the value of the reactance X, so that the input power factor is unity. Input power factor will be unity when supply voltage and the supply current, when they are in phase, then only we can say that this whole circuit from the input side is a unit power factor. So for that to happen, what is the reactance? What is the value of the reactance we need to figure out, so that the input current and the input voltage are in phase, so that the whole circuit appears to the input side as a pure resistive load. So let's solve this numerical. So please listen carefully. This question is a very conceptual question. So I have drawn this figure again. See, this is the voltage source. It is the AC voltage source and the resistance is 1 ohm. We need to find what is the element and its reactance value. So this is the turns ratio of the transformer. This is a single phase transformer. Turns ratio is 2:1. So the voltage across the load is 110 volt. The power factor of the load is 0.89 and the power absorbed by the load is 4 kilowatt. So here let me assume the current here drawn by the load is I2. So therefore the current drawn by the load is I2. So now the power absorbed by the load is 4 kilowatt and the voltage we know 110 volt and the power factor of the load is 0.89. So we need to find what is the amount of current drawn by the load. So this is a single phase load, right? So power equation is P is equal to VI cos phi. P is equal to VI cos phi. Suppose it is a 3-phase load, then P is equal to root 3 VL IL cos phi. But this is a single phase load, so that is the reason P is equal to VL IL cos phi. Your voltage is 110 volt and the current we need to find, and remaining thing all things we know. So therefore the power drawn by this load, so for P is equal to V into I into cos phi, where V is equal to voltage across the load and I is the current through the load and cos phi is the power factor of the load. So the power of the load is 4 kilowatt. So therefore 4 into 10 to the power of 3. Here voltage across the load is 110 volt. And here current through the load is I2, that we need to figure out, and the power factor of the load is 0.89. This is the power factor of the load. Now the only unknown parameter is current I2 through the load. So therefore I2 is equal to 40.8 ampere. So therefore if you solve this, you will get I2. The current drawn by the load is 40.8. I have already told you, whenever the current drawn by the load, then there will be another current which is drawn by the transformer, so that it will make suppose if there is a current drawn, so therefore the net flux will decrease, because of this there will produce a small amount of flux which will oppose the original flux. So therefore the resultant flux will decrease. So therefore this transformer, the primary will take more current, so therefore it will make the flux to its original value. So therefore this current is I2 dash. Suppose this current is I2, then this current is I2 dash. We can figure out this current I2 dash by MMF balance method. I have told previously also. So therefore by MMF balance method, we are going to calculate what is the value of the I2 dash. So therefore the primary terms is N1 and the secondary terms is N2. So therefore by MMF follows I into N. So therefore by MMF, the primary MMF is I2 dash N1 is equal to secondary MMF is current into turn. So therefore current is I2 and the turns is N2. So we need to find what is I2 dash. So therefore I2 dash is equal to I2 into N2 by N1. So N2 by N1 is N2 is 1 and N1 is 2. So therefore 1 by 2. So therefore I2 by 2. Here I2 we know 40.8. 40.8 by 2 is 20.4. So therefore I2 dash is equal to 20.4 ampere. These are the magnitude values. So therefore the current drawn by the load is 40.8 ampere. So for the current drawn I2 dash is equal to extra current which is drawn by the primary, so that it can make the flux to its original value, which is 20.4 ampere, which is drawn by this one. So now we know the voltage across the load is 110 volt. So let me assume this is E2. This is the voltage. So the voltage induced across the secondary is also E2 because these are both are in parallel. So therefore E2, because the EMF induced across the secondary is E2 and the voltage across the load is 110 volt. Because they are connected in a parallel fashion, because they are connected in parallel, so they are actually the same voltage, right? 110 volt and E2 both are same. So therefore E2 is equal to 110 volt. So therefore the voltage across the load and voltage across the secondary winding is again E2. E2 is equal to 110 volt. So now we need to find what is the EMF induced across the primary winding, E1. So we know simple E1 by E2 is equal to N1 by N2. So therefore E1 by E2 is equal to N1 by N2. So E1 is we need to find. So therefore E1 by E2 is how much? We know E2 is already 110 volt. So 110 volt. N1 by N2. N1 is 2 by 1. So therefore if you do the simplification, we will get E1 is equal to 220 volts. So the current through the load I2 is equal to 40.8 ampere and the current I2 dash is equal to 20.4 ampere and the voltage E1 is equal to 220 volt. Now we will write the phasor representation of all these parameters. So see here suppose here this one, right? This is the flux direction. So if you take phi is equal to phi of sin omega t, but EMF induced E1 is equal to N into d phi by dt. If you do that, we will get EMF equation will always lead the flux voltage. So therefore E1, this is the E1 will leads the flux in the core by 90 degrees. So E1 and E2 will always oppose each other. E1 and E2 will always oppose each other. So therefore this will be the E2 direction. This is the E2 direction. So we know for a load the voltage and the current are going to get a lagging. This is the lagging load, right? So therefore cos phi is equal to 0.89. So now the cos phi is equal to 0.89. So therefore phi is equal to cos inverse of 0.89. So we will get cos inverse of 0.89. If you do, we will get phi is equal to 27.12 degree. So here phi is phase angle between the voltage across the inductor and the current voltage across the load and the current through the load. Here phi is equal to phase angle between the voltage across the load and the current through the load. So the voltage across the load is E2. E2 is equal to 110 volts. So therefore the voltage across the load is E2 and the current through the load. So it's a lagging load. So therefore current I2 is going to lag the voltage across the load by 27.2 degree. So therefore the current here I2. This is actually this current is the current here. The current is I2. I2 is going to lag the voltage by phi. Phi is how much? Phi is actually 27.5. This is a phi. Phi is equal to 27.12 degree. So here I2 and I2 dash are in an opposite direction. E1 and E2 are in opposite direction. I2 dash and I2 are also opposite direction. This we will learn in the theory classes. So E1 and E2 are opposite, and I2 dash are opposite. Opposite means in this straight line. So therefore this will become straight line, right? Straight line means this straight line. We need to draw a straight line. So this is the I1, I2 dash. This is I2 dash. This one, I2 dash. So here phi means here also same angle phi. So therefore here also same phi, because corresponding angles are equal. Same straight line. So therefore this angle phi and this angle is corresponding angle. So therefore the angle between them is same. So now this is the primary current, right? This is the primary current. This is, let me assume this is I1. So therefore now let me assume this is some reactance element. So now this current, let me assume this is some I is equal to, so therefore the current is voltage across this element by the reactance of the element. So voltage across the element is E1 and the reactance is X. So for I is equal to V by X. I am calculating the magnitude value. So E1 is equal to how much? E1 is equal to, we already know, 220 volt by X. So for the magnitude of the current through the element is equal to 220 by X. So we have calculated the current through this element. Suppose let us assume this element as an inductor. Suppose I assume this element as an inductor, this reactance as an inductor. So if I assume this element as an inductor, so therefore the voltage across the inductor, the current through the inductor has to lag the voltage across the inductor by 90 degrees. So the current has to lag the voltage across the inductor by 90 degrees. So therefore the current is going to lag here. So therefore this is the I. This is going to I through the reactor element. So I assume this element as an inductor element. So therefore the current has to lag the voltage even by 90 degree. So therefore this I1 is equal to sum of, by KCL, I1 is equal to sum of I2 dash plus I. So therefore I2 dash vector plus I dash. So therefore now we need to do the vector sum of I2 dash plus I. I2 dash is this one and I is this one. We need to do. So therefore this is I and this is I2 dash. So if you do here, you will get like this. This is the current I1. So here I1, right? This is I1. So I1 here, current and the resistor, across the resistor the current and the voltage are in phase. So therefore current is, where is 1 and the current is I. So the voltage is equal to current into resistor, means I1 into 1. So therefore I1. So therefore the voltage here, the net voltage V is equal to voltage E1 plus the voltage across this one is again I1. So therefore these both are in phase. So therefore I1 is here. So now I am going to write this also I1. So now V is equal to E1 bar plus I bar. So if you do this one, we will get like this. This is the voltage. But they are asking, we need to get a unit power factor. Unit power factor means voltage and the current has to be in phase. But we are getting voltage and the current are not in phase. So therefore our assumption is wrong. The voltage vector is this one and the current to the source is I1. They both are not in phase. So therefore our assumption, we have assumed that the element is an inductor. So therefore our assumption is wrong. So now we will assume another case which is capacitor. So therefore we are going to remove all these things. V1 and this is phi, right? So same things I am going to add here. This is phi, this is E1. So this is I am removing this one. So listen carefully, it will be very easy. So now I am assuming this as a capacitor. Now I am assuming the thing is capacitor. So therefore same thing, I1 bar is equal to I2 bar plus I bar. So now if for capacitor, the voltage across the capacitor, this is the current to the capacitor I. So therefore current has to lead the voltage by 90 degree. So therefore this is the voltage, right? So therefore current has to lead here. This is the current, right? this is the current I, capacitor, this is I. So this current is going to lead the voltage by 90 degree. So now we need to do the summation of vector sum of I dash and I2 bar. So therefore if you do, now we need to get a unit power factor, unit power I2 dash. Now I am going to do the component here, see carefully here. Now it will become I2 dash cos phi, and this will become I2 dash sin phi. So when these two components are equal, so therefore the net current is equal to I1 is equal to I2 cos phi. So this will be the net current. This will be net current. When this will be a net current I1 is a net current. So therefore when these two currents are equal, right? So therefore I is equal to I2 dash sin phi. So therefore this is a net current, right? So therefore now the voltage across the resistor is 1 into I1, means I1. So now current is I1, voltage and current are in phase. So therefore the net voltage V is equal to E1 plus I1. E1 is already we know E1, and I1 is again in this direction, right? I1. So therefore the net voltage is again also in the straight line. So therefore the net voltage and the input current I1 are both are in the same straight line, means they both are in phase. So therefore our assumption that is a capacitor is satisfied. I am repeating again if you are confused. Here I equated these two terms I2 and the opposite, the vector component I2 dash sin phi. So therefore the net current is in this direction, upward, but the voltage across the resistor is I1 into 1. So therefore I1. So therefore this is a I1. Here if E1 plus I1 is equal to supply voltage. So supply voltage and the supply current are both are in phase now. So that is the reason now by this, when we assume it is a capacitor, then only this will become a pure resistor, means cos phi unit power factor across the supply. So therefore now we need to do I is equal to I2 dash sin phi. I is the current through this element. So therefore which is already 220 by X is equal to I2 dash. I2 dash we already know I2 dash is equal to 20.4 sin phi. Sin phi means sine of 27.12 degree. So if you do the simplification, we will get X is equal to, this is a capacitor, right? So XC is a capacitor element. So XC, whether you write X or XC, nothing happens. We will get answer 23.61 ohm. So what I am trying to do is, what I am trying to say is, this is a capacitor. Then only the whole circuit will become a resistor across the. So that is why we need to, whenever it is a capacitor, then only the supply voltage, which is a summation of E1, and this is a length, this length is I1. Summation of E1 and I1. I1 is 1 into I1, so that's why this voltage is I1. So summation of these two things is straight line, and similarly the net current is again I1 is also, both are in same phase. That's why it is a unit power factor. The answer is 23.61 ohm. I hope you understood this numerical. So by this lecture we have completed 10 numericals of electrical machines, which are the previous year gate questions, and we will do in the upcoming lectures in the same manner. If you are facing any problem in these lectures, the numericals which you have discussed, then please do comment in the comment section. If any problem, if you are facing not understanding, if you not understood any of the numerical, then please do comment the question number in the comment section, and we will see the comment and we will do the repetition of that numerical again in the coming lecture, so that it will be understood in a very clear manner. If you like the content of our video lectures, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video, that notification comes to your mobile.